In this video I want to show you an engineering problem. It is about the 4-bar linkage. That's what it's called. It is some kind of mechanism and I will sketch it here. We have some kind of rod which is connected to some hinge here, a pivot, whatever you want to call it, and this is the point O around which this rod can rotate. Then we have another connection here at the point A, and then we have another body here which is a connecting rod. We have another pivot here at the point B, and then we have another rod here, and by the way this is called a crank, and also in this case, since this is a parallelogram, this is also a crank. And here we have another connection with the ground, and this is the point C. We have also other points. In particular, I'm interested in the center of mass here, G1. So this is the body number 1. Then we have the body number 2. And here we have the center of mass G2. And here we have the center of mass G3. So in particular, we know that the length OA is equal to the length OB, and OG1, for example, is equal to OA over 2. Similarly for CG3, which is equal to OG1, which is equal to OA over 2, and AG2 is equal to AB over 2. So these are midpoints, G1, G2, and G3. Then we have some forces which are acting from the outside on this mechanism, on this 4-bar linkage. We have a force Q, an external force Q acting on the point G2. Then we have some torque acting on this first crank, OA, and we will have to find the torque. I'm not going to draw the torque here, but you have to guess that there is some torque applied to the rod OA, the crank. And then we also have some actions due to the weight of these rods. So there is some force here, which is the mass of this first rod times G, applied at this point G1. Similarly, here we have mg, and the masses of the cranks will be the same. That's what I assume. They're exactly the same. So the length is the same and also the mass is the same. And then here, if we assume that Q does not contain the action of the weight, we also have the mass of the second body, the connecting rod, and let me call it capital M times G, right? And what we want to find is we want to find the action that we have to apply to the crank OA to keep the balance of the forces. So we want to find the torque, and let's assume that OA is rotating in this manner with an angular velocity omega, so it's a clockwise manner. And the unknown is the torque M that we apply to the first crank. So we need to find the magnitude and also the direction of the torque. So you might say, well, it should be in the same direction as omega, but it's not. So let's say it's not to be taken for granted. We have to show the direction, and we will find that M will go in the opposite direction actually, so it is breaking the mechanism. And well, let's start. I will solve this problem in two ways. First, I will consider the simpler way, which is by using the so-called virtual work principle, VWP. So this virtual work principle is simply an energy balance. So we have the torque m dot product with the angular velocity omega, plus then we have q dot product with the velocity d, the velocity vd of the point here. So I'm going to call this point d, or if you want, is g2. So vd or vg2, plus then we have mg dot product vg1 plus mg dot product vg3, and then we have capital M G dot product Vd, and according to the virtual work principle, this is simply the derivative with respect to time of the kinetic energy that I'm going to call capital T. And by the way, we are going to assume that omega, the angular velocity omega, is a constant. Okay, so the mechanism is rotating in a uniform manner. Now, the kinetic energy of this mechanism, this 4-bar linkage, capital T, will be given by twice the kinetic energy of the crank. So let me call it Tc plus the kinetic energy of the connecting rod. Let me call it Tcr. And, well, we can easily find these two kinetic energies. So the kinetic energy of the crank is simply equal to 1/2 times the moment of inertia around the point O. It is the point around which the crank is rotating, and then we get omega squared. Whereas the kinetic energy of the connecting rod, Tcr, is simply equal to 1/2 the mass of the connecting rod times the velocity of the point d squared. Why is that? So in this case, for the connecting rod, we don't have a rotational part, because this is a simple calculation. So we can show that actually the angular velocity, we can call it omega AB, let's say, to indicate that it's the angular velocity of the connecting rod, or maybe we can call it omega 2. Omega 2 is equal to 0. Why? Well, because if you think about it, since this is rotating in a uniform motion, the angle which this line connecting the points AB with respect to the x-axis is always 0, because CB is equal to OA. So this is an easy way to see this. It can also be proved more rigorously, but I will not do it. It's quite intuitive. So the angular velocity of this rod, this connecting rod, is 0, which means that we can simply calculate the kinetic energy like this: 1/2 the mass of the body times the velocity of the center of mass squared. And the velocity of the center of mass, Vd, so it's also easy to understand that Vd will be equal to Va, the velocity at the point A, since the angular velocity is 0, and Va is very easy to calculate. So Va is 1/2 m times Va squared, but Va is OA times omega, and this is squared. So we already have a formula there. And we can easily see that if omega is a constant, we assume that omega is a constant, then the derivative with respect to time of the kinetic energy is 0, right? So we can simplify our virtual work principle. Then let's also consider the first crank. So this is the point O. This was the point that we called A, right? Yes, it's the same notation. Then here, if we draw the force Q, that we know it is applied to the point D, but let's assume that we can draw Q here, and if we draw the velocity D, Vd, which is equal to Va, well, we know that it is perpendicular to OA, and Va is equal to, or yeah, Va or Vd, because they are the same, is equal to the angular velocity omega cross product the vector OA. So that's why it's perpendicular to OA. It's a cross product with one of the vectors being OA. So it's perpendicular to OA. And this angle here, let's call it theta. And therefore, this angle here is also equal to theta, if you think about it. And this means that Q dot product VD can be written as Q omega OA cosine theta. And then we also have to calculate mg dot vg1. So we have a force mg here, and similarly, in a similar fashion, this is mg dot vg3, and this is mg omega OA over 2 cosine theta, right? It's very easy because vg1, which is a velocity here, vg1 is simply equal to omega cross product OG1, and the length of OG1 is OA over 2. So that's why we have this formula. Then we have capital M G dot product VD, and this is just mg omega OA cosine theta. And now from the virtual work principle, we obtain m dot omega equal to minus, and then we have m plus capital M G plus Q omega OA cosine theta. From here, we see that we have this minus sign, which basically means that M goes the opposite direction with respect to omega. So this is a breaking torque. It's breaking the mechanism, the 4-bar linkage. So if we consider the magnitude of M, at first let me draw M here. So M should be directed in the opposite direction with respect to omega. So this is the vector M. The magnitude of M, let me write it in black. So we have M equal to M plus capital M G plus Q. Then we don't have omega here because we can simplify with this. And then we have OA cosine theta, like this. This is the final result. This is due to the fact that M and omega are parallel to each other, but going in opposite directions. So they are perpendicular to the plane. But omega, since omega is directed clockwise, so it's clockwise, it means that M is coming out of this plane. So usually it's denoted with this point here. And then omega is going inside. So usually this is denoted with a cross like this, but never mind, this is just notation. And so that's the result. But I also want to show you another way of solving this problem, which is a little bit more complicated, but it won't take us too long to find the solution. We want to find the solution by using free body diagrams. Let me sketch here the second body. So this is the connecting rod. Here we have the point A, and at the point A we have some reaction force, and the reaction force will have a component along y and a component along x. So F12x, I will call it F12 because it's the force that the first rod is applying to the second body, the connecting rod, F12, and it is the x component, so it's F12x. Whereas here we have F12y. After you do the calculation and you insert the values of the parameters, you might find that, for example, this is negative, and therefore it means that the actual direction of this force goes along this direction, is this one. But it doesn't really matter. You can choose a direction, and then based upon the result that you get, if you get a minus sign, if you get a negative result, you will know that the direction will be this one instead of this one here. And similarly for f1,2y, it doesn't matter. Then here we have the point D and we have Q. We also have capital M times G. And at the point D, we also have some inertia force due to the acceleration of the point D. Because even if the second body here is not accelerating, does not have an angular velocity, it does not mean that it is not accelerating. It is actually accelerating. The point D is accelerating. It has some acceleration, which is directed actually in this manner, more or less like this, and the force will be centrifugal, so it will go the opposite direction. Let's call it, well, this is just the mass of the body times AD, so this is the inertia force, and it is just equal to m times the magnitude of the centripetal acceleration, which is omega squared OA. This is the only acceleration that we have. It is centripetal. There is no other acceleration because omega is a constant. So I will not delve into the details of this, but the acceleration of this point is equal to the acceleration of the point A. And the acceleration of the point A can be obtained by considering the first rod. And this point here, the point A, is accelerating inwards. So it is accelerating with a centripetal acceleration that's moving, that's directed along this line OA. So it's going towards the point O. And we don't have another component which is perpendicular to this one, simply because omega is a constant. If omega were not a constant, we would also have another component of the acceleration. So that would complicate it a little bit, but I'm not going into the details of this. I've already calculated some generic formulas in other courses on classical physics and rigid body mechanics. So I will not discuss the details of this in this video. I will assume that you know how to calculate this force. It's just m omega squared OA. And then similarly, we have another reaction force here at this other point that I called B, right? And I will split the reaction into two different components. So we have F32X going this way, and then we have F32Y going this way. Okay? Then let me also draw the velocity of the point D. So this is VD, and remember this angle here is theta. And this force MAD describes an angle theta here with respect to the horizontal line. So this line here wants to be horizontal. So this is horizontal. And so this is the free body diagram. We will calculate an equation from here, so we can calculate the moment with respect to the point A. I will do it later. Let me also draw the first rod. So actually, let me draw the second rod. So this is the second rod, so this is the point C, and this is the point B. And we have, at the point G3, we have mg, and we also have the force, a centrifugal force directed in this manner, and it is m omega squared OA over 2. Now we also have to draw the forces F32Y, so pay attention to this detail. Here F32Y will go up, because here it goes down. Since this is an internal reaction, here the force should go up if in here it goes down. Basically, it is the third law of dynamics. If there is a force acting on a body and one force from one body to the other goes this way, then the other body will react with an opposite force. It is equal in magnitude but opposite in sign. And then we have to draw f32x in this manner, just like this. So now we can write down some equations. In particular, let's calculate the moment with respect to the point C here for the second crank, the second this is the third body or the second crank, and we get OA sine theta f32x, which is basically, so OA is equal to CB. CB times sine theta, and theta is here, will give me this length. So this length times f32x will give me the moment generated by this force with respect to the point C. And I will consider a positive sign here for torques, or in this case I should say moments directed clockwise. Then we get minus OA cosine theta f32y, because in this case for f32y the length that I should consider is this one with respect to this axis, and this is just CB times the sine, the cosine of theta, but CB is equal to OA, so I can write OA here, and then we have plus mg OA over 2 cosine theta, the moment generated by mg, and this is equal to 0. Then we can write down an equation for the x-axis. We have f12x plus mad cosine theta minus f32x equal to 0. So it's an equation along x for this body. Then we can write down an equation along y. f12y minus q minus mg minus f32y plus mad sine theta equal to 0. And finally we can write down an equation still for this body, but we will calculate the moment with respect to A. The moments with respect to A, we can write minus AD sine theta MAD. Then we can write plus AD Q plus MG plus 2AD F32Y, and this is equal to 0. So in this case 2AD is equal to AB. It is simply this length here. And we have 4 equations. In particular, what I can write down, these 4 equations is, first I can find the F32Y from this one. So F32Y is equal to MAD sine theta minus Q plus capital MG over 2. Then I can write F12Y from this one, which is equal to Q plus Mg plus F32Y. So I can write it from here. So I have plus, I can write MAD sine theta over 2 minus Q plus Mg over 2. And then I also have minus MAD sine theta. And if I put these two together, this one with this one, and this one with this one. Here I get q plus mg over 2, and then I have minus mad sine theta over 2. And I can also write down the expression for f32x from here. f32x is equal to, let me write it actually from here. So let me write f32x from here. f32x is equal to f32y times actually minus mg over 2 divided by the tangent of theta. So you can rewrite it in this manner. And we have found the expression for f32y. So we can rewrite this expression like this. We have m ad cosine theta over 2 minus q plus mg over 2 tangent theta minus mg over 2 tangent theta. And finally, from here, we can obtain f12x, which is equal to minus mad cosine theta over 2 minus q plus mg over 2 tangent theta. And then we also have minus mg over 2 tangent theta. Finally, after we find all these expressions, we can consider the free body diagram for the first crank. So this is the point O, and this is the point A. We have f12x here and f12y here, like this. And now let's assume that the torque that we have to apply, let me call it m, like before, is in the opposite direction as omega. And at the end, we will find that indeed this is the case, as we should expect. So here, if we take the counterclockwise motion as positive, it means that we have m minus, let's calculate the moments with respect to the point O. Remember that we have also the force mg here. We also have a centrifugal force here, but we don't care about it because it will not generate any moment with respect to O. So we have minus OA over 2 cosine theta mg minus OA cosine theta f12y plus OA sine theta f12x, and this should be equal to 0. Now, if you substitute the expressions for f12y and f12x, here you will easily find that m will be equal to m plus capital M g plus q times OA cosine theta, which is exactly the expression that we wanted to find. So this was a little bit more complicated because we had to draw all the free body diagrams and calculate these expressions here from the equations that we wrote down. Whereas by using the virtual work principle, it is more convenient, so it is simpler. But I wanted to show you both ways because it will probably deepen your understanding of this kind of the physics, of the classical physics that's behind these engineering subjects, these engineering topics.